Today we're going to start a new topic. For the first time this semester we're going to talk about unsupervised learning methods and techniques, okay? But before we begin, what I wanted to point out is one thing that I forgot to do in the previous class. Okay, remember what we just finished was logistic regression, right? And we did one problem, pretty much. It was predict which ones of my bank customers will agree to take a loan out of the bank when we offer it to them, right? And what type of predictors did we use? Most of them were continuous, right? Income, age, experience, etc. But there was one predictor which we used that was categorical, and that was education, right? So, therefore, we need to expand our tool matrix. So, if you still have it, you're supposed to have the handout that I gave you, right? So, we're dealing with supervised technique, right? The logistic regression, and we're predicting the categorical response. 0, 1, right? If the customer will get a loan from the bank or will not agree to a loan from the bank. And here's what we did in the previous couple of classes, right? We discussed a lot how do you use continuous predictors in this model, right? But in the previous class, we said you can also use categorical predictors, right? So therefore, what I'm going to do is copy-paste logistic regression, okay? So it's still a supervised learning. My target is categorical variable, 0, 1, but my predictors can be categorical as well. Okay? They can be continuous, or they can be categorical, or it can be mixture of both continuous and categorical predictors. Okay? So our matrix kind of starts to fill up a little bit. Okay, so with that being said, let's switch gears a little bit. All right? Let's talk about unsupervised, because we have a big void here, right? We didn't discuss unsupervised methods. Okay, and the only thing that we're going to discuss in this class is clustering analysis. Okay, I did post the slides out there on Scholar about clustering, so let's go ahead and kind of talk about clustering in general today, right? What's clustering? Clustering essentially it's a very simple thing. Okay, I have a lot of observations in my data set. Now remember when we discussed databases and data sets, we said they contain data sets contain variables, right? It can be target variable or predictors. We also call them attributes and also call them columns, right? What's in the column is one variable, right? Every record, every row, horizontal row that we have in the database essentially is a data point. Okay? So for example, let's say I have a record of students at CNU. There is a table, right? And what are the columns in this table? Student ID, student name, email address, major, home address, right? Social security number, etc., etc. These are all columns, but every row contains information about individual, specific, particular student, right? That's a data point. So specific record with ID number 00501366. First name John, last name Smith, social security number 1, 2, 3, 4, 5, 6, 7, etc. Right? This is data. This is one record in my database. That's a data point. Okay. So clustering. The idea basically is the records in my database. I want to group together records in my database, and each group I want to contain records that are as similar to each other as possible. Okay, that's basically the idea. Right? So I may have in my database thousands, millions, or even billions of records. But if I want to cluster them, essentially what I'm saying is, how can I select out of all the records, groups of the records which are very similar to each other? Then I have to define what do I mean by similar, right? For example, let's say I have two different records about students, right? One has the major in finance, another has the major in accounting, right? But they took some courses are similar, right? They took, for example, accounting 201, 202, accounting 301, 302, 303, etc. Another is finance. He took also accounting courses, right? Plus business core. And then he took some other courses, finance 324, 325, etc. Some courses are same, some courses are different. Are they similar records or are they not similar records? How do I define that, right? So here we need to define basically how do we differentiate, or how close to different records to get, okay? But let's kind of discuss what are the clustering applications. Believe it or not, clustering applications is not a new idea. In fact, most of the ideas that we discussed, and we're still going to discuss this semester in this class, are not new. Data analytics as the area is booming right now, right? So you may have an impression that this is happening as we speak, right? The new methods are being developed. Clustering, for example, is a new method. Classification tree that we looked at is a new method. No, they're not, okay? Classification trees were around for decades. Regression that we discussed was known since, 1950s probably, okay? A logistic regression, which we just finished, also a well-known, well-established model, okay? So none of the material that we're discussing these days in this class is new, okay? It was not developed yesterday or in the last 5 years or in the last even 10, 20 years, okay? We as a humanity knew these methods long time ago. Why they became so hot all of a sudden? Well, they became so hot because we have huge computing power in our hands, okay? So before that, it was just academic interest. We couldn't do much with data. Nowadays, when we have huge storage, very quick computers and very quick networks, now we can do something about them, right? We have quick algorithms that can process large volumes of data. That's why it became popular these days, okay? It's kind of a right time and the right place kind of thing, okay? But clustering. Biology, especially zoology, right? If you take zoology deals with classification of animals, right? There is like animal kingdom, right? And then there are subtypes, and then there are families, and then there are species, etc., etc. So there is like hierarchy structure, right? So every animal we can classify, right? We can put them in the category, right? For example, let's say we have a cat. Cat belongs to like kingdom, animals, then subtype mammals, then there is family of like feline, right, and then species, blah, blah, blah. So when you arrive to this last classification node, it groups together animals that look similar, right? Cats, like your regular cat, which you have at home, then there are lions, tigers, leopards, puma, right? They all belong to the same family, right? They're just different species, right? So we cluster them together. So biology deals with that, okay? Chemistry, periodic table. How many of you took chemistry before? In university or at school? Okay, you obviously studied periodic table, right? What's the deal with periodic table? Why it was such a breakthrough in the 19th century? What's so cool about periodic table? It organizes elements according to their properties, right? Now, to give you an example, I know a little bit about that because, after all, I have a physics degree, right? So, periodic table looks like a table and it has rows, right? And there is like first row, second row, third, fourth, etc. And it has groups, right, or columns. So how many columns are there? I believe there should be, let's see, 6, I believe, right? In the first 2 rows, there are, first row contains actually 2, right? There is hydrogen and there is helium, right? What's the deal with hydrogen? Hydrogen is highly reactive element, right? It can create a compound with virtually anything, right? If you put hydrogen and oxygen together, what do you get? The water, right? So hydrogen is very active element. Helium is passive element. In fact, it's called inert gas, right? It has no compounds, right? You cannot create any molecule that will contain helium. Right? This is a self-sufficient element, okay? So in the first group, basically, in the periodic table, contains highly active elements. The next one, I believe, is like sodium and then potassium, right? These are so active that, I don't know if you ever saw that. I remember that from high school. Like, our teacher actually showed us this experiment. So she had this sodium. Sodium is a metal, right? So, and it's very pliable, so basically you can cut it with a knife. So she basically cut, a little bit of sodium and just drop it into the water. Bam! Immediate reaction, right? It reacts with water. It's so active, okay? And then here you have, what's after helium? I forgot. Is it argon, neon, right? That's probably neon, right?
Neon, argon.
Yeah, neon, argon, AR, right? Argon. All these are inert gases, right? They don't create any compounds. And basically in between them we have also transitionary kind of elements, right? So as you move from one group to another group, like this, right? Then you're getting the chemical elements which are less and less chemically active, right? Until finally you arrive to the group of elements that is completely inactive, right? So therefore, every group of elements, right? Every vertical group, every column of the periodic table contains elements which are behaving in a very similar fashion. Chemical, right? They have similar physical properties. They have similar chemical properties. So chemistry, essentially, when it comes to properties of elements, deals with clustering, right? Periodic table is another example of clustering, okay? Then there are multiple business applications, obvious, right? First, in marketing, obvious application, right, from marketing. Let's say I want to find out, I'm running a retail business, right? And I want to find out who are the most likely customers to whom I can advertise successfully lawnmowers, okay? Who will buy lawnmowers from me? Well, I don't know. What I can do essentially is look at all the transactions. Let's say I'm running a hardware store, right? And different people buy different stuff, right? They buy tools, they buy letters, paint, plumbing supplies, and some people buy lawnmowers, right? So I can basically go ahead and take a look at the lawnmowers, the transactions that constitute lawnmowers, and try to find what's the most common thing between them, right? So what's my most typical profile of the customer who buys lawnmowers? Or alternatively, I can just go ahead and take all transactions and say, let's group them together. Let's run this algorithm, clustering algorithm, and whatever comes out, right? It may be that I'll have group of records which are similar. In what sense? Like, let's say people who buy, when they do grocery shopping, they buy frozen pizza, beer, and bananas, right? And I don't know, toothpaste, for example, right? So what's common between these people? And then I can profile them, right? So I can say, hey, these are similar records, which seems to be very, very close transactions. They look alike, right? One record is like another record, somewhat. So what's common between all these people? Maybe they are over a certain demographic, like, for example, between the age 25 and 45. Maybe they all make over $50,000. They have master's degree. They have, college loan payment, etc., etc. They have 2 children and a dog, right? That's my basically customer profile, most typical customer who buys lawnmowers. And then after that, I can create marketing campaign which is targeted for specific users, right? So instead of creating the mass mailing and just mail it to everybody, right? I can go ahead and say, hey, this is a typical profile of a customer who buys lawnmowers. So how about that? I'm going to sift through the records in my database, find customers who match this profile, and mail the special on the lawnmower just to them, right? So I can create more customized, more targeted marketing campaign. Balancing stock portfolio. Remember probably from finance. What's the first rule of finance? Starts with D. Diversify, right? What does that mean, diversify? Don't put all the eggs in one basket, right? Don't bet on just one stock, hoping for the best, right? So buy stocks with high risk, for example, and high return. Buy stocks also with medium risk and medium return, and buy low risk stocks. So therefore, if high stock risk go down, then your losses will be limited, right? Diversification, okay? How can I diversify? Well, same thing, right? I can have a history of prices for different stocks, okay? And then after that, I can go ahead and say, let's group them together. Let's see which stocks behave similarly. Prices go up simultaneously, or prices go down, or whatever other measure I'm going to pick, like measure of the stock volatility, right? Standard deviation of the price, or beta measurement, okay? Or earnings per share measurement, right? So some things that are used in financial industry. And then I can group stocks together and I say, hey, look, this is the group of stocks which has similar parameters, right? Similar price, earning per share ratio, or beta characteristic, or something like that, right? So they behave similarly, therefore, if I want to balance my portfolio, I should pick some stock from this cluster, some stock from that cluster, etc. And then I create balanced portfolio, right? So clustering has a lot of applications. Okay. So let's now discuss clustering methods. See, when it comes to clustering, there is no such thing as this is absolutely the best thing to do. So in this class, this semester, we're going to discuss two methods. Okay, one of them is called hierarchical method, and that basically the idea is there are two ways how you can cluster together observations using hierarchical method. There is agglomerative way and there is disaggregative way. So we're going to look at agglomerative way. What's agglomerative way? Let's say I have 100 different items, just for simplicity, okay? And I'm starting with a point where every single item is a cluster of one, okay? And then after that, on the first step, I'm going to say, out of these 100 different clusters, which ones are closest together? So I have to somehow measure the distances between observations, right, and find the smallest. And if I found the smallest distance, then I'm going to merge these two observations together and call them a new cluster. So therefore, I'm starting to merge observations, right? Closest observations together are starting to form groups or clusters. So I do that in iterative process, okay? So that's why they're called hierarchical. So on the next iteration, I'm going to measure new distances, right? And find the smallest and do another merge. So therefore, my clusters are getting bigger and bigger and bigger, and I have less and less and less of the clusters. Until finally, on the last step, everything is in one cluster, right? And then I have to set up kind of my cutoff point. I'm going to say, well, I don't want to have one cluster, everything together. That's obviously not my goal, right? And I don't want to have every observation by itself, right? Cluster of one. I want to be somewhere in between. So I'm going to set, like, let's say I want to have 10 clusters. Then I'm going to see the moment when I have only 10 clusters, and that's going to be it, okay? So that's how hierarchical method works. Non-hierarchical method, we're going to use k-means method, something that's called k-means. In other words, right off the bat, I'm going to say, well, I want to have 7 clusters, okay? And then I'm going to throw some initial points into the, I think that first, this point is going to be the center of cluster 1. This point is going to be the center of cluster 2. This point is going to be the center of cluster 3. Then I'm going to measure the distances from points to the centers and assign them to the clusters. Then recompute the center of the cluster again, recalculate the clusters, and I'm going to do that again and again and again until finally I'm done. So, but this method basically says I have to decide, non-hierarchical method, k-means, right? I have to decide right off the bat how many clusters I'm going to have. But this method is somewhat simpler, and later we're going to discuss in what exact way. Okay? Oopsie. All right. So what's kind of the main feature of the clustering technique is that it's an unsupervised method. In what sense? We don't have a target column, target variable. Okay? It's not like we're trying to predict who will take the loan or who will not take the loan, who will drop out of the university or who will stay in the university, or how many cars I'm going to sell based on my prices. Nothing quite like that, okay? I'm essentially using all of my columns together simultaneously. So there is no single target column. There is no target variable. So from that standpoint, this is an unsupervised learning, okay? All right. So let me actually show you an example. You know what? Just to put that somewhat in perspective, right? Go ahead and log into Scholar, right? Just for the heck of it. And in the jump files, I believe I posted utilities right there. Okay, so download the file utilities. Okay? And open it up in jump. Just to kind of give you an idea, right? What do I mean exactly by clustering? Look at that. So this is a very small data set, right? It contains information on what? 22 utilities companies, right? What do we mean by utilities? Well, electricity producing companies, right? Companies that generate electricity and sell it to consumers, right? So company is in Arizona, Boston, etc., right? So these are locations, I guess, right? And then there are 1, 2, 3, 4, 5, 6, 7, 8 different columns. How do I call columns? Variables, right? Or attributes, okay? Now, columns are different, right? Fixed means what? Do I have a description? Yeah. Fixed charge coverage ratio, income over debt ratio. So that's financial term, right? Okay, cool. Then I have return on rate of return on capital. Then I have cost of 1 kilowatt that they sell, right? 1 kilowatt per hour, right? That they sell. Load factor. I don't know what that means. I guess how many customers they supply per year, or what's their peak load during the day, or something like that. Okay. Then demand. Demand probably is how many customers they supply, or how many kilowatt hours they sell, right, to the consumers, right. And then sales in terms of dollars, I'm guessing, right, or millions of dollars, whatever it is. What does it say? Percent demand growth. That's different, right. So in other words, year to year, I'm experiencing some growth in sales, right, and that's basically that's what it tells me. Okay. Then nuclear, percentage of electricity that they generate by nuclear plants, and fuel cost per 1 kilowatt per hour. So how much money they spend to generate 1 kilowatt per hour, right? Very different columns, wouldn't you agree? Some of them deal with sales in dollars. Some of them deal with growth in terms of percentages, right? Some of them deals with financial ratios, such as debt or income over debt ratio, right? Very different units of measurements, right? Very different numbers. So what I'm going to try, I guess, here is see which companies are close together. If I consider all these 8 measurements, so I'm not looking at just sales, for example, or just the cost, right? So there is no target variable from that standpoint. I'm looking at all 8 columns simultaneously. So, for example, this company in Arizona and this company, Central, number 1 and number 3, are they close? Are they similar? Well, I don't know. Fixed, for example, the first one, 1.06 versus 1.43. Is it close? Well, probably closer than this one, I guess, right? 0.89 is far away from them, right? Then 15.4 versus 9.2. That's probably a big difference, right? 151 versus 113. That's a big difference, probably, right? So these may be not so close, right? So I'm looking across all the columns, essentially, when I'm defining the distance between 2 observations, how close or how far away they are. I'm looking across all the columns, right? All the variables, not just one. That's why this is unsupervised learning technique, okay? I'm not targeting any one column. I'm looking at all of them simultaneously. And you know what? Let's do this. Let's do the chart, okay? We're humans, right? We live in 3-dimensional world, but we can't even interpret 3-dimensional plots, right? So the most that we can do is 2 dimensions, x and y. So let's do x and y. So how about that? Let's go to the graph and do the graph builder, our good old friend, which we used at the beginning of the semester, right? So how about this? I'm going to construct 2-dimensional, what's it called, by the way, if I draw one continuous variable versus another continuous variable? How do I call that? Starts with S. Scatter plot, right? Scatter plot. Okay, so I'm going to plot cost, for example, horizontally. Okay. You know what? Fuel cost. Let's do the fuel cost. So how much money it takes to generate 1 kilowatt hour, right? And the sales. Okay. Sales I'm going to do vertically. Okay. And just get rid of this squiggly thing. All right. So these are all of my 22 observations that I have right there. Okay. So now you tell me, do you see any observations that are kind of closer together and further away from the rest of them? Which ones? True or false? These 4 kind of stand out, right? There is a big distance between them and the next group, right? So therefore, if I would have to find companies that are close together, I would say that's my first cluster, right? And these companies, what characterizes them as far as the fuel cost is concerned? High versus low? Low fuel cost. And the sales? Higher sales, right? That's a good combo, right? The cost of operations is low and the sales are high. That's probably a good combo, right? Then I have this group right there, in the middle kind of, right? These, I think I'm going to group together, these observations. They have also kind of low-ish fuel cost, wouldn't you agree? And they also have low-ish sales, right? So they're not doing that great. And then there is a third group, which is right here, I believe. They kind of stand out by themselves. These are high cost, low sales, right? That's a bad combo, obviously, right? The cost is high, the sales are low, so that's not as cool, right? So you can see the principle, right? Observations that are closer together, I want to group together and so that they form clusters, right? Okay. Now let's take a look at question. Next question is, how do I define distance, right? In order for me to be able to say these two are close together as opposed to these two are not close together, I have to be able to measure the distance between observations. Okay, so ladies and gents, flashback from, I don't know, high school or maybe Math 135, calculus, right? So let's say I'm going to be simplistic, okay? I'm going to be simplistic. Let's say I have only two measurements, x and y. So there is my point 1, and this point has, let me write a little one right here, coordinates x1, y1. And there is a point 2 right here, and 2 has coordinates x2 and y2. I can connect them with a straight line, true? Any 2 points I can always connect with a straight line, yeah. And that basically is going to be the distance between one point to another point. So can you tell me what's the distance between point 1 and point 2? Do you remember the formula? Remember what's it called? Pythagorean theorem, right? So the basis of this Pythagorean theorem is right triangle, correct? Like this. So this is my x1, and this is my x2. This is my y1, and this is my y2, right? So in Pythagorean theorem, what do we have? If I take the square of this side, let's call it A, side A, and I have square of this side, side B, then it's going to be the third side squared, right? So the rule, if I call this C, A squared plus B squared equals C squared, right? So therefore C, which is distance from 1 to 2, is the square root from A squared plus B squared, right? So A equals literally x2 minus x1, right? x2 minus x1, and I have to square that, okay? And B equals to y2 minus y1, and I have to square that as well. Oopsie. And that's going to be the distance between 2 points, 1 and 2, right? It's also called Euclidean distance, Euclidean distance. Okay? So that's one way to measure the distance. Make sense? Problem is, let's go back to my file. Here is the problem, okay? Let's take a look at all of my measurements. So essentially what I can do is treat every record. So let's say this is my first record, right? How many components or columns do I deal with? Well, 1, 2, 3, 4, 5, 6, 7, 8 components. So therefore, my first record has how many coordinates? 8 coordinates, right? Each number is a coordinate. x1, x2, x3, x4, x8, okay? Second point, same thing, 8 components, y1, y2, y3, etc., right? So therefore, I should be able to expand my formula, right? This is distance, Euclidean distance for a 2-dimensional case. What if I have more dimensions? Well, if I have more dimensions, then the formula just keeps going, right? And after that, I'm going to have x, k, let's call it z1 minus z2, right? Squared. And all of that is under the square root sign, obviously, right? So therefore, however many columns I have, that's going to be part of my formula for calculating the distance, right? But the problem is then becomes, look at the numbers. Fixed cost, they are all mostly between 1 and 2, correct? They're not high, okay? Second, which is what? Return on, rate of return, right? Now they're also around 10, more or less, right? Which column provides me with the highest numbers? Like, highest values? Sales, right? Sales are in terms of, I don't know, dollars or millions or thousands of dollars, whatever it is, right? So what will happen is, when I'm going to compute the distance, can you guess which one is going to be dominating? sales, right? Because sales is gigantic number, right? Difference between the sales are measured in terms of like thousands, right? In my present units of measurements. When I square that, it becomes even larger. So therefore, it's going to pretty much kill everything else, right? So therefore, I have to be careful when I define distance, right? So if I don't want the sales to be a dominating factor just because they're measured, right? And what if I measure them in cents, not in dollars? Jesus Christ. It's going to be a gigantic number, right? It's going to be absolutely killing everything else, right? So therefore, what happens oftentimes is when people perform clustering analysis, they basically say, well, instead of using these numbers, let's normalize them. Let's create a standardized version of it. It's like what you remember probably from statistics, right? Z, standardized score, is equal to x minus the mean divided by the standard deviation, right? We can do the same thing. We can look at all the sales, for example, right? Find the standard deviation, find the average, okay? And do this formula, okay? So subtract the sales minus the average sales and divide by the standard deviation, and that's going to be probably a number anywhere between, I'd say, -3 to +3, most of them, right? So therefore, we're going to kind of scale every variable so that the variables that are measured in like high numbers, they're not dominating anymore. But that's one way to do the distance, okay? It's called Euclidean distance. That's not the only way. So let's discuss some other ways. Way number 2 is called Manhattan distance. How many of you have been in New York City? You walked in Manhattan area? So how is Manhattan organized? It's organized like this, right? It has all these avenues intersected by all these streets, right? The corner of the 5th Avenue and 25th Street, right? So it's basically a rectangular grid, right? So therefore, Manhattan distance, here's what we mean by Manhattan distance. What if I want to go from this point, intersection of the 5th and 9th Street, right, to this point right there, intersection of 7th and 31st Street, whatever it is. I can't go directly through the buildings, right? So therefore, that would be, by the way, if I go straight through the buildings, kind of, right, like a Superman, what kind of distance I'm going to cover? Starts with E. Euclidean distance, right? That would be Euclidean distance. But I can't go this way, right? Well, what I can do is I can go until this intersection, number 2, and then right there to number 3, right? And that's called Manhattan distance, okay? So, therefore, as opposed to Euclidean distance, Manhattan distance is like this. Between 2 points, right? I have to take x1 minus x2 absolute value. So essentially, this horizontal piece, right, which I called A, plus absolute value of y1 minus y2, okay? So essentially, this distance, which I called B, I believe, in the previous one, right? That would be y1 minus y2. That's Manhattan distance, okay? Just a different way to measure the distance between 2 points, nothing more, okay? Sometimes this one is better, sometimes the other one is better. The choice is pretty much up to you, okay? Also, let's discuss actually the property of the Manhattan distance as compared to Euclidean distance, okay? Now, this is something called triangle inequality. If I have triangle, let's just do any triangle, okay? A, B, C. So this side I'm going to call little a, this side I'm going to call little b, and this side I'm going to call little c. Here is what triangle inequality is, okay? It's purely mathematical statement, kind of. In triangle, okay? Always, whatever triangle you have, always, sum of 2 sides is going to be greater than or equal to the third side. So if I take a plus b, it's always going to be c or more, okay? If I take a plus c, it's going to be a plus c. Tell me. Greater than or equal to b. If I take b plus c, it's going to be greater than or equal to a, right? So triangle inequality. In triangle, sum of 2 sides is always greater than or equal to the third side. Now, why do we have equal sign? What in the hell? Well, here, right, let me give you an example. Let's say I'm going to flatten my triangle really badly, okay? So, here, this is my C, and this is my A, and this is my B, okay? still sum of A and B is going to be greater than C, right? What if I flatten it even more? What if my triangle looks like this? Still the case, right? What happens if I keep flattening my triangle? Eventually my point C is going to be right here, right? And my triangle will become a line, right? And in this case, A plus B will be what? Exactly equal to C, right? That's in the case of kind of extreme case, flat triangle, right? But if triangle is not flat, if triangle looks normal like this, then greater than is always going to be the case. Sum of two sides is always higher than the third side, okay? Well, let's go back to our previous picture, okay? Here's my Manhattan distance, right? So this is what we discussed, Euclidean distance, right? That's my square root from x1 minus x2, all these things squared, right? The formula that we had before, okay? So, what can you tell me about the relationship between Manhattan distance and Euclidean distance? Which one is higher? Manhattan distance is always great, right? Why? Because of the triangle inequality, right? Because A plus B is always greater than C in the triangle, right? C is my Euclidean distance, right? That's hypotenuse, right? A and B are parts of Manhattan distance. So if I add them together, that's adding two sides, it's always going to be higher than the third side, okay? So Manhattan distance is always greater than or equal to Euclidean distance, okay? How are we doing? Make sense? You're awfully quiet. Say meow. No. Well, is it rain? Okay. All right. So, and let's discuss the last one. Correlation-based similarity. Okay? Now, correlation-based similarity. Now, note that everything that we discussed so far is the distance between 2 points, right? I have point 1, I have point 2. How do I find distance between them? There is more than one way to do this, right? So the third way is correlation-based similarity. Let's kind of have a discussion of this, all right? So let's say I have 2 points, right? 2 records in my database. Like, for example, 2 records about the power generating companies, right? So one company is in Arizona, another company is Central, okay? And I have all these 8 columns, right? Column 1, 2, 3, etc., right? So this is my x1, x2, x3, etc. Last one is x8, okay? This is my y1, y2, y3, etc. And the last one is y8, okay? What I can do actually is I can treat these numbers, the pairs of numbers, okay, as points. All right? So this is my point number 1, this is my point number 2, etc. And what do I do with points when I have x and y coordinates? We just discussed that. I can plot them, right? And that's going to be what? If I plot them, x versus y. Starts with s, a scatter plot, right? Okay, cool. So my first point is going to be x1, y1. Let's say it's right here, okay? That's point 1. Second point is whatever it's like. Rate of return, what was that, right? x2 and y2. Let's say the point is right here, okay? Third point, let's say it's right here. Okay, well, let me actually do a little bit of creative drawing here. So that's going to be point 4, that's going to be point 5, that's going to be point 6, that one is 7, and 8 is going to be right here, okay? So I have a bunch of points, right? So I'm going to erase the numbers actually because they're useless. Oopsie. So this is the scatter plot essentially, right? Of just 2 points. Arizona power generating company and Central power generating company. What can I compute about two different scatter plot? My 2 variables x and y. If I have scatter plot, I can compute how correlated the observations are. Remember when we discussed linear regression, we said if you have variable x and variable y, you can compute the coefficient of correlation between them, right? Now remind me, coefficient of correlation is a number between what and what? 0 and 1. -1 and +1, right? So it's -1 and +1. In what case my coefficient of correlation is positive 1? Well, here, right? If my points perfectly align across the positively sloped line, right, then I have coefficient of correlation equals to +1, right? That's extreme case. Very good, actually, case, right? If my points, on the other hand, are forming a line which is negatively sloped like that, then my coefficient of correlation is -1, right? Okay, cool. But if my coefficient of correlation is 0, remember what picture it corresponds to? It means that I really have no pattern, right? It looks like a cloud of points, therefore I can draw my line in any way, like this, or like that, or like this. It's all the same pretty much, right? So there is no correlation. Knowing X does not give me any knowledge about Y, okay? So, going back, all right, right here, okay? So, therefore, if I organize my just two companies like that, I can always construct the correlation coefficient, right? I can always calculate the coefficient of correlation between just two observations, right? In my set, between the company in Arizona and between the company in Iowa, for example, okay? And I'm going to use that as the measure of closeness, right? So, ideal case is when things are correlated, right? Remember we discussed that. When things are perfectly correlated, that means that these points behaving similarly, right? So therefore the distance between them should be equal to 0, right, from that standpoint. So here's what I'm going to do. I'm going to say distance between 2 points is equal to 1 minus the coefficient of correlation between these 2 points squared. So look what's going to happen. What if my points are perfectly correlated? In other words, they are located, hold on, let's say they're perfectly positively correlated. In other words, they form straight line like this, right? So I plot all these pairs of points, x1, y1, x2, y2, and they form perfect straight line, okay? That means that one company is like another company but scaled up or down, right? All the measurements, they behave really, really similarly, right? The rate of return goes up for both companies simultaneously. Sales are also kind of related in the same ratio, right? So they form really nice looking straight line. In which case the coefficient of correlation is going to be +1, right? And I want to call these companies similar because they behave similarly, right? All their financial characteristics and sales and costs and all of that, it's in perfect ratio with each other, right? So in this case, probably I want them to belong to the same cluster, right? Because their behavior is very similar, right? It's like one is scaled in another company, right? Everything looks very similar with some coefficient, right? So therefore, what will happen is, if I square the coefficient of correlation, it becomes 1, right? And what's the distance between these two companies? 1 minus 1 equals 0, right? On the other hand, what happens if I have just cloud of points like this, random cloud of points, okay? So I have two companies again, I form points out of columns, right? And I plot the points, and it looks like random cloud. No trends, no lines, it's not positively sloped, it's not negatively sloped. In fact, when I calculate the coefficient of correlation, it's 0. It means that companies don't look like like each other at all, right? All of their characteristics pretty much scattered randomly, all over the place, right? So therefore, they probably are not similar, and from that standpoint, they should not belong to the same cluster, right? So therefore, the distance between them should be high, right? So, in this case, what's the distance between 1 and 2? 1 minus the coefficient of correlation squared, coefficient of correlation 0, so the distance is 1, right? So, if I define my distance that way, then I will cluster together similarly looking companies, which are kind of, their readings of all different measurements, they're kind of correlated with each other, right? They behave similarly. So that's just another way to define distance. It's a correlation-based distance, okay? So there is more than one way to do that. Okay, so we discussed 3 ways to define distance, right? Manhattan distance, Euclidean distance, and correlation-based distance, right? Between 2 points, right? Now, in the next class, we're almost out of time today. In the next class, what we're going to do is we're going to discuss, remember when I told you, when you have hierarchical clustering, what you do is you start merging points, right? At some point, you may arrive to the case when you have 2 clusters and they're close together and you have to merge them. So, next question is, We can measure distance between the points right here. We just discussed that, right? How do you define distance between clusters of points? Close clusters versus far away clusters. And that's coming next time. Okay? Okay, we're done for today.